Hello, and welcome to Space for Sleep. I am so glad you are here. Tonight, we deep down through the vast silent expanse of the cosmos. Our Milky Way drifts like a cosmic island, a swirling sea of hundreds of billions of stars bound together by gravity, dancing through the darkness, and yet, far beyond the veil of our night sky, another giant waits, the Andromeda Galaxy, our nearest spiral neighbor, shining faintly through the distance, moving closer with every passing second. It is an inevitable journey, a slow-motion dance of destruction and rebirth, written into the very fabric of time itself. We often think of galaxies as still, eternal, frozen in their celestial beauty, but the universe is not still. Every star, every world, every galaxy is in motion. And the Milky Way, as majestic as it appears, is speeding through space at hundreds of kilometers per second, pulled by unseen forces and carried by cosmic tides. Out there, Andromeda is doing the same. Two galaxies, two titans of light and matter, slowly drawn together by gravity's relentless pull. In 4 billion years, they will meet. Not in a moment of collision like crashing cars, but in a breathtaking ballet spanning millions of years, a dance so vast that it transcends our imagination. Tonight, we will explore what happens when these two galaxies collide. What will become of the stars, the planets, the black holes, and the fragile spiral arms that now define our cosmic home? Will our solar system survive the encounter, or will it be cast adrift into the endless dark? The answer lies in understanding the nature of galaxies themselves, these vast structures of stars, gas, dust, and dark matter. Though they appear solid from afar, galaxies are mostly empty space. If you could shrink the Milky Way to the size of a dinner plate, the nearest star to our sun would be another grain of light placed hundreds of kilometers away. This emptiness is the key to the survival of stars during galactic collisions. When galaxies merge, their stars rarely collide directly. Instead, they weave past one another, their gravitational fields twisting and warping the structure of each galaxy. It's not a crash, it's a cosmic waltz, the night sky of future Earth, if humanity still exists to witness it, will transform beyond recognition. Andromeda will grow brighter with each passing millennium, a glowing spiral that slowly swells until it dominates the heavens. Eventually, its arms will stretch across the sky, brighter than any full moon, until the two galaxies begin to merge into one vast, radiant storm of stars. But to truly understand what's coming, we must first journey through the past, to see how galaxies like ours are born, how they evolve, and how their fates are intertwined by the invisible hand of gravity. This is the story of the Milky Way's destiny, the grand future awaiting our cosmic home. In the beginning, before galaxies had names, before stars had formed, the universe was a sea of formless energy. The Big Bang had just occurred, and from that primordial explosion came space, time, and the raw ingredients of everything that would ever exist. Hydrogen and helium, the simplest elements, filled the cosmos. For hundreds of millions of years, the universe was dark. No stars burned, no galaxies shone, only the faint afterglow of creation drifting through expanding space. But then, slowly, gravity began to work its quiet magic. Tiny fluctuations in the density of matter pulled gas together, forming the first clouds, and within them, the first stars ignited. Light returned to the universe. These first stars were enormous, unstable, and short-lived, exploding in brilliant supernovae that forged the heavier elements, carbon, oxygen, iron, the building blocks of life and planets. Their explosions sent shockwaves rippling through space, seeding new generations of stars, each born from the ashes of the old. Over billions of years, these stars gathered into vast rotating disks, the first galaxies. And among them, deep in a quiet corner of the cosmos, our Milky Way began to take shape. It didn't form all at once. Galaxies grow like living things, by consuming smaller ones, merging, and evolving. The Milky Way's story is written in these ancient collisions. It has devoured dozens of smaller galaxies, tearing them apart and absorbing their stars. Even today, faint streams of stars, remnants of ancient mergers, wrap around the Milky Way like ghostly trails. This is the nature of galaxies. They are cannibals, feeding on one another to grow. And somewhere out there, Andromeda has been doing the same. Roughly the same age as our galaxy, Andromeda too has grown through cosmic violence, merging with neighbors, forming new stars, and shaping its vast spiral arms. Both galaxies are now mature giants, each with a central supermassive black hole anchoring its core. These black holes are the hearts of galaxies, regions of infinite density where gravity crushes everything into a single point. In the Milky Way, our central black hole, Sagittarius RO, is 4 million times the mass of our Sun. In Andromeda, the black hole is even larger, a monster of roughly 100 million solar masses. When these galaxies finally meet, their central black holes will spiral toward each other in a deathly embrace, releasing unimaginable energy as gravitational waves. But that ending lies far in the future. For now, the Milky Way and Andromeda are like two dancers moving slowly across a vast stage, drawn together by the invisible rhythm of gravity. The space between them is immense, over 2.5 million light-years. Yet, at a speed of nearly 110 kilometers per second, Andromeda is closing the gap. Every second that passes brings the two galaxies infinitesimally closer. We don't feel it, we don't see it, but the motion is real. It's written into the cosmic dance of everything around us. When they finally meet, it won't be a sudden impact, but a long, beautiful chaos, a slow intermingling of stars, clouds, and dark matter that will reshape both galaxies forever. Before that moment comes, though, countless stars will continue their journeys, countless worlds will orbit in peace, and our Sun will continue to shine, a small, steady light in the ocean of the Milky Way. But 4 billion years is not an eternity. In cosmic time, it's just around the corner, and as that moment approaches, our night sky will begin to change in ways both terrifying and breathtakingly beautiful. The first hints will be subtle, a faint glow in the constellation of Andromeda, a slightly brighter patch that astronomers of the future will watch grow decade by decade. Humanity, if it endures, will witness the sky transform into a living mural of galactic light. As millions of years drift by, the night sky will begin to evolve in ways no human alive today could imagine. The familiar constellations, Orion, Cassiopeia, the Big Dipper, will shift slowly out of shape as our solar system continues its orbit around the galactic center. But one new feature will begin to dominate everything: Andromeda. At first, it will look like a hazy patch of light, brighter and larger than it appears now. Astronomers in that distant future will measure its motion and confirm what we already know today, that Andromeda is coming for us. Thousands of years later, the patch will swell into a grand spiral visible even to the naked eye. Its arms, glowing with billions of stars, will stretch across the heavens brighter than any moonrise. Imagine standing beneath that sky, a cosmic panorama where two galaxies face each other like reflections in the dark. Slowly, over millions of years, Andromeda will grow enormous, filling 1/3 of the sky. The view will be surreal, two spirals drifting closer, their forms shimmering across the night, their light mixed with the faint haze of countless suns. It will be the most magnificent sight any civilization could ever witness, and perhaps the most humbling. Yet behind that beauty, chaos is brewing. Gravity, the architect of everything we know, will begin to distort both galaxies. As their halos of dark matter overlap, invisible tides will tug at their outer stars. The delicate spiral arms of the Milky Way will start to twist and warp. Some stars will be flung outward into intergalactic space, forming long, thin streams that stretch for hundreds of thousands of light years. Clouds of gas and dust will collide, compressing and igniting bursts of new star formation. Entire regions of both galaxies will blaze with newborn suns, a stellar renaissance born from destruction. But the space between stars is so vast that few, if any, will collide directly. Instead, their orbits will shift under the immense gravitational forces, creating waves of energy that ripple through the galactic disks. If intelligent beings are still living on Earth by then, they will see this transformation unfold slowly over generations. Each millennium, the stars will appear in slightly different positions. Andromeda's core will brighten, splitting the night in two. Eventually, the galaxies will pass through one another for the first time. It won't be a single crash, but a series of encounters spanning millions of years. The first passage will be violent but spectacular. Both galaxies will stretch into long tidal tails, vast ribbons of stars and gas curling away into space. The Milky Way's once perfect spiral shape will be torn apart, becoming distorted and chaotic. The gravitational tug-of-war will hurl entire clusters of stars into deep space, while others will fall toward the combined center, where the two supermassive black holes begin their slow approach. For a while, the galaxies will separate again, drifting apart before gravity pulls them back for another encounter. Like celestial lovers, they will dance back and forth, each pass drawing them closer until their cores finally merge. During this process, the Sun and its planets will continue orbiting, mostly untouched, though their paths will be altered. The night sky from Earth, or whatever remains of it, will blaze with new light. Nebulae will shimmer, clusters will form, and the heavens will glow brighter than ever before. The stars we see today will fade into new constellations, replaced by unfamiliar patterns shaped by a galaxy reborn. It will be the end of the Milky Way as we know it, but not the end of beauty, for what will emerge from this cosmic collision is something even grander, a new galaxy, larger, more luminous, and more powerful than either that came before. Astronomers of the future already have a name for it: Milkomeda, the giant elliptical galaxy that will rise from the union of the Milky Way and Andromeda. When the first encounter finally begins, it will not come with a sudden flash or explosive noise, but with a slow distortion of the heavens. From any vantage point within either galaxy, the process will seem almost supernatural. The spiraling arms of Andromeda and the Milky Way will stretch and twist as tidal forces tug at their outer regions, distorting their shapes like ripples in a pond after a stone has been cast. Stars will begin to migrate from their familiar orbits, drifting into elongated streams that arc across the cosmic dark. Imagine entire solar systems, stars with their planets intact, being flung hundreds of thousands of light years away, cast adrift between galaxies. These orphan systems will wander through intergalactic space, carrying with them any life that might exist upon their worlds, silent travelers in the infinite night. As the galaxies approach one another, the interstellar clouds of gas and dust will begin to collide head-on. Unlike the stars, which pass mostly unharmed through the vast emptiness, the gaseous regions will interact violently. The compression of these colossal clouds will trigger an era of furious star formation. Billions of new stars will ignite, lighting up the galaxies like a cosmic fireworks display. This will be a period of rebirth and chaos, where the night skies of countless worlds will blaze with the glow of newborn suns. But along with this beauty will come instability. The gravitational tides will distort planetary orbits, hurling some worlds into cold exile while sending others spiraling toward their suns. Even so, the scale of these events is so immense, so drawn out, that from the perspective of any one civilization, it would seem as if nothing were happening at all. Thousands of generations could pass before the movement of stars became truly noticeable. Yet from the grand perspective of time, everything is changing. The Milky Way's graceful spiral arms will stretch into vast plumes of light, curling outward like tendrils, while Andromeda's disk begins to warp and fracture. The combined gravitational field of both galaxies will form immense tidal bridges, streams of stars connecting one to the other, shimmering pathways of light across millions of light years. Somewhere within this chaos, our Sun will continue its long orbit. Astronomers predict that by the time of the first encounter, about 4 billion years from now, the Sun will already have evolved into a red giant. Earth's oceans will have boiled away, its surface scorched and barren. Whether humanity survives elsewhere among the stars or fades into history long before this event, the universe will continue without pause. The merger will proceed in silence, unbothered by the fate of any single world. After the first passage, the galaxies will drift apart slightly, their motion slowed but not stopped. The gravitational energy of their interaction will cause both to lose their original spin, transforming their elegant spiral forms into more amorphous shapes. Then, drawn together again, they will fall back toward each other for the second encounter. Each collision will bring more chaos, more mixing, more stars flung into intergalactic exile. In time, the two central black holes, the beating hearts of both galaxies, will begin their slow, inevitable dance toward one another. These two titans, millions of times more massive than our Sun, will orbit each other in tightening spirals, their immense gravity distorting space and time itself. When they finally merge, they will unleash a burst of gravitational waves that will ripple across the cosmos, faint whispers in the fabric of reality, echoing the end of one era and the birth of another. After billions of years of movement, distortion, and merging, the chaos will settle. The once grand spiral structures will dissolve into a smooth, elliptical form, the new galaxy that astronomers today call Milkomeda. The stars will orbit in random patterns rather than neat spirals, and the night sky will look entirely different from anything we know now. Yet even in that future, light will continue to shine. The merged galaxy will contain trillions of stars, glowing softly in the darkness, a monument to the forces that shaped the universe. What began as two separate islands of light will become one, vast, ancient, and eternal in its beauty. As the galaxies continue their slow embrace, deep within one of the spiral arms of the Milky Way, our Sun will live out the final chapters of its long existence. The Sun, by that time, will be nearly 9 billion years old, a weary star nearing the end of its stable life. Long before the true merger takes place, it will already have begun to change. Stars like our Sun do not burn forever. Over time, they consume the hydrogen in their cores, fusing it into helium and releasing energy that has warmed our planet for billions of years. But once that fuel runs low, the balance between gravity and pressure begins to fail. The core contracts and heats up, igniting new fusion reactions in the surrounding layers. The result is dramatic. The Sun swells into a red giant, expanding far beyond its current size. Its outer layers will engulf Mercury and Venus and may even reach the orbit of Earth. If Earth still exists, its surface will be scorched into molten rock, its atmosphere stripped away. Oceans will have long since boiled off into space. Our planet, once vibrant and blue, will become a barren glowing ember beneath a swollen red sun. Farther out, the gas giants, Jupiter and Saturn, will remain, their moons bathed in dim red light. The icy worlds of the outer solar system, like Pluto and the Kuiper Belt objects, will briefly thaw before freezing again once the Sun sheds its outer layers. When the red giant phase ends, the Sun will collapse into a white dwarf, a dense, Earth-sized remnant, glowing faintly with the last of its stored heat. Around it will drift the remnants of its former self, a ghostly planetary nebula, expanding slowly into the void. By then, the great galactic collision will be underway. The sky around the Sun, if any eyes remain to see it, will be unrecognizable. Instead of the thin band of the Milky Way stretching across the heavens, the entire sky will be filled with light. Vast arcs of stars, remnants of tidal streams, will illuminate the darkness. Andromeda's luminous core will merge with ours, painting the sky in endless waves of color and motion. Our sun, now a pale ember among countless billions, will continue to orbit within the merged galaxy, its path altered by gravitational tides but largely undisturbed. Even as the galaxies collide, the chance of any two stars striking one another remains vanishingly small. The distances between them are so vast that, though entire galaxies collide, their stars merely dance between one another in a silent ballet. The real drama unfolds not in collisions of stars, but in collisions of gravity, in the invisible tug-of-war shaping every orbit, every trajectory, every pocket of light. Our solar system may find itself flung into a new orbit far from its birthplace, carried to the outer regions of Milkomeda, or even expelled into intergalactic space. If that happens, the Sun and its few remaining planets would drift alone between galaxies, wandering the dark forever. Yet whether cast away or captured, it would still remain part of this grand cosmic story. One small light among trillions, a witness to the universe remaking itself. And in that far future, long after Earth is gone, and the sun's light fades, the legacy of our world, our species, and our observations of the heavens might still echo in the universe's memory, perhaps stored in the electromagnetic whispers we've sent across the stars. But the story doesn't end there, for while our sun fades, the collision will spark the birth of countless new stars. The merging clouds of gas and dust will collapse under gravity, igniting new suns, new worlds, and perhaps in time new forms of life. The death of one age will give rise to another. From the ashes of the Milky Way and Andromeda, creation will continue, because in the universe, every ending is only a beginning in disguise. Out of chaos comes creation. As the Milky Way and Andromeda tear through one another, the great clouds of gas and dust that once formed calm spiral arms will collide and compress, birthing a new generation of stars. In the vast voids between ancient suns, immense shock waves will ripple outward, stirring the raw materials of creation into motion. Entire regions of space will ignite with light as new stars burst into being. The collision will become one of the greatest waves of star formation the universe has seen in billions of years. To an observer within the merging galaxies, the night sky will shimmer with newborn brilliance, blue-white stars blazing intensely for a few million years before burning out in violent supernovae. These explosions will enrich the surrounding space with heavy elements: carbon, oxygen, nitrogen, iron, the building blocks of planets, oceans, and life. The merging galaxies will become a vast stellar nursery, glowing with clusters of brilliant light. This era will mark a rebirth, a transformation from two spirals into one great elliptical galaxy, rich in energy and possibility. In the aftermath of the collision, regions once calm and dark will now be alive with nebulae, new suns, and the swirling disks of emerging planetary systems. Within those disks, microscopic dust grains will collide and stick together, forming pebbles, rocks, and over millions of years, planets. Some will become rocky worlds like Earth, others gas giants like Jupiter. Around these new stars, conditions will vary, some too hot, others too cold, but somewhere in between, in the gentle warmth of a sun-like star, life may once again find a foothold. The seeds of existence, forged in the hearts of dying stars, will scatter and settle across the new galaxy. The same physics that shaped our world will shape theirs. The same chemistry that made our oceans and air will flow through alien worlds beneath alien skies. The cycle continues: death, rebirth, and renewal. Even as our sun fades into memory, new suns will rise, carrying forward the legacy of light. But not all that is created will last. Many of these new stars will be massive, burning through their fuel in just a few million years before collapsing into neutron stars or black holes. The galaxy will sparkle with their brilliance, then fall quiet again as they vanish into darkness. Over time, the rate of star formation will slow. The once turbulent galaxy will begin to settle, its energy fading into a quieter, more stable form. Milkomeda, the remnant of the collision, will no longer have the graceful spiral arms of its parents. Instead, it will be a smooth, elliptical giant, a golden sphere of stars glowing softly in the night. To any civilization that arises within it, the sky will be rich but different. There will be no clear band of the Milky Way crossing the heavens, no thin streak of light. Instead, the entire sky will shimmer evenly with countless stars in every direction. The center of the galaxy will blaze with concentrated brilliance, the home of the merged supermassive black hole, now 100 million times the mass of our sun, quietly feeding on the gas and dust that wander too close. Around it, an accretion disk will glow with fierce radiation, a beacon visible across the cosmos. The collision will have ended long ago, but its story will live on in the stars, in the orbits of worlds yet to form, and in the faint gravitational whispers left behind. And somewhere, in that future galaxy, there may be beings, descendants of life that once looked up at the Milky Way, who will study the stars of their night sky and wonder where they came from. They will not see the same constellations we know. They will not know Earth or the Sun or Andromeda as separate things. For them, it will all be one, a single vast home in the cosmic dark, and maybe, through their telescopes, they will look outward across the universe and see other galaxies far away, and ask themselves the same question we ask tonight. What happens when galaxies collide? At the very heart of this colossal union, where light itself bends under the weight of gravity, two titans will begin their final dance. For billions of years, the Milky Way's Sagittarius AF and Andromeda's massive central black hole will have circled each other, drawn together by the merging tides of stars and dark matter. They are the ultimate architects of their galaxies, ancient engines of destruction and creation. Each one millions of times more massive than our sun, each one silently shaping the orbits of stars for eons. When the galaxies collide, their cores will not meet immediately. They will spiral inward slowly, like predators circling before the strike. Surrounding them, the dense swarm of stars and gas will form a glowing, chaotic heart, a region of extraordinary violence. Gravitational forces will sling stars around at incredible speeds, some ejected entirely from the galaxy, others pulled inward to feed the black holes. The two monsters will draw closer, orbiting one another at a distance measured in light years. Each orbit will bring them nearer, each pass stripping away energy through gravitational waves, ripples in the very fabric of space-time. These waves will spread across the cosmos, stretching and squeezing the geometry of the universe itself. For the first time since their birth, the two black holes will truly feel each other's pull. The final moments of their approach will be a cosmic crescendo. As they spiral faster and faster, their immense gravity will distort space-time so violently that even light will twist in their wake. The accretion disks surrounding them, swirling halos of gas and plasma, will flare with blinding radiation. Jets of energy, powered by magnetic fields and spinning matter, will erupt from their poles, shooting across interstellar space for thousands of light years. To an observer watching from afar, the galaxy's core will appear to pulse with unimaginable brightness, the beating heart of a universe in motion. Then, in a moment lasting only seconds, after billions of years of slow movement, the two black holes will merge. The collision will release a burst of gravitational energy unlike anything since the dawn of time. The universe itself will tremble. Space will ripple, time will stretch, and for an instant, the cosmos will remember its own birth. No light will escape from the final merger, only invisible waves traveling across the infinite, carrying the signature of the event to the farthest galaxies. Billions of years later, civilizations across the cosmos may detect those faint ripples, studying them as we do now, piecing together the story of how Milkomeda came to be. The merged black hole, now a single giant, perhaps 100 million times more massive than our Sun, will settle at the center of the new galaxy. It will dominate the gravitational landscape, shaping the orbits of trillions of stars, controlling the flow of matter and time in its domain. Around it, a glowing accretion disk will form, radiating energy as gas falls inward. From its poles, twin jets of high-energy particles will streak across the galaxy, shining like cosmic lighthouses. Over millions of years, as the galaxy stabilizes, the energy output will fade. The chaos will quiet. The central black hole will rest, its hunger satisfied, surrounded by the swirling remains of its parent galaxies. And yet, this final act of merger is not destruction. It is creation. The energy unleashed will stir the surrounding gas, triggering one last wave of star formation. The central region of Milkomeda will glow for eons with the light of new stars born from the ruins of the old. What began as two separate cosmic cities will now be one, a single luminous empire of light bound by gravity and time. To future astronomers, the story of its birth will be written in every orbit, every stream of stars, and every echo of gravitational energy still rippling through space-time. And to any beings who look up at the sky from worlds yet unformed, the heart of their galaxy will be a beacon, a reminder that even in destruction the universe never truly ends. It transforms, evolves, and begins again. When the violence finally subsides, when the last shockwaves of gravitational energy fade into the cosmic background, the newborn galaxy will emerge from the storm. Its shape will be unlike either of its parents. The delicate spirals that once defined the Milky Way and Andromeda will be gone, replaced by a vast glowing ellipse of stars. Milkomeda will rise as a golden giant, smooth and rounded, its light soft but immense, stretching across hundreds of thousands of light years. From a distance, it will resemble the great elliptical galaxies we see today through our telescopes. Featureless at first glance, yet filled with ancient beauty. Up close, it will be a realm of incredible complexity. Billions of suns moving in random orbits, no longer confined to the neat disk of a spiral. In this new galaxy, motion itself will seem chaotic, but within that chaos lies balance, the gravitational equilibrium of a system that has finally found peace. The center of Milkomeda will shine brightest. Here, the merged, supermassive black hole will rest like a hidden sun, wrapped in glowing clouds of gas and stars. Around it, entire clusters of stars will whirl in tight orbits, moving at unimaginable speeds. The innermost region will radiate with soft golden light, the signature glow of countless ancient suns nearing the end of their lives. Farther out, the stars will thin into a vast halo, peppered with faint globular clusters, ancient remnants of the Milky Way and Andromeda, still orbiting like ghosts from another age. Dark matter, the invisible scaffolding of the cosmos, will envelop Milkomeda in a massive halo stretching far beyond its visible edge. It will hold the galaxy together, shaping the orbits of its outermost stars and anchoring its structure against the slow pull of cosmic expansion. From within, the view will be breathtaking. To any observers living on a world inside Milkomeda, the night sky will no longer show a thin band of light. Instead, it will be filled on all sides with a dense, even glow. The heavens will shimmer with thousands of bright stars, closer, larger, and more numerous than anything seen from Earth today. The galactic core will dominate the sky, a luminous sphere that never sets, bathing distant worlds in a soft golden haze. In that far-off epoch, the universe will also be older, its light dimmer, its energy fading. Distant galaxies will be receding faster and faster as cosmic expansion continues, and the night sky beyond Milkomeda will slowly empty. The great clusters of galaxies that once surrounded us, Virgo, Coma, Perseus, will drift away beyond the reach of light. Eventually, Milkomeda will stand alone in a vast, dark void, its stars shining in solitude. The universe, once crowded with galaxies, will grow silent around it. But within that isolation, life and light will persist. The new stars formed during the collision will live for billions of years, illuminating their planetary systems with steady warmth. Some of these worlds may be rich in the elements of life, forged in the supernovae of earlier generations. On one of those worlds, under a sky blazing with the golden light of 1 trillion suns, new eyes may look upward and wonder what came before, why their galaxy glows so evenly, why the stars move as they do, and what lies beyond the fading horizon of space. They will not know the Milky Way or Andromeda as names. They will know only their single home, the great elliptical realm that gave them light. And if their astronomers are clever, if they study the motions of the stars and trace the faint tidal streams that still weave through their galaxy, they may discover the truth. They will find evidence of ancient collisions, arcs of stars, disrupted clusters, and the faint gravitational scars left behind. From those clues, they will reconstruct the story of 2 spiral galaxies that once existed, 2 families of stars drawn together by destiny, whose meeting gave birth to their world. And perhaps they will realize that even in the far future, when the universe grows cold and dark, every galaxy carries within it the memory of all the others it has ever touched. Time, in the aftermath of creation, stretches into unimaginable lengths. The newborn Milkomeda settles into calm, its stars finding equilibrium, its chaos quieting into an ancient rhythm. Billions of years pass, and the galaxy begins to age. The brilliant blue stars, born in the violence of collision, burn out first. They live fast, die young, and end as neutron stars or black holes, their brief radiance replaced by silence. The smaller, yellow and red suns endure, glowing steadily for tens of billions of years. The galaxy grows redder, dimmer, and more serene. What once blazed with youthful energy now glows with the warm light of age. Outside, the universe continues to expand. The space between galaxies stretches faster and faster, driven by the mysterious force we call dark energy. In the beginning, Milkomeda still shares the cosmos with countless neighbors, great clusters and filaments of galaxies connected across space. But as time goes on, that vast web begins to tear apart. The more distant galaxies accelerate away until their light can no longer reach us. The cosmic horizon shrinks. One by one, the lights of the universe go out. In 100 billion years, Milkomeda will be alone, adrift in an endless sea of darkness. Beyond its borders, there will be nothing to see. No distant spirals, no faint clusters, no cosmic background radiation bright enough to detect. The universe will appear finite once again, isolated by the speed of its own expansion. Within this lonely galaxy, evolution continues quietly. The remaining stars orbit the central black hole in slow, graceful patterns. Some merge, forming larger suns, others fade into white dwarfs, brown dwarfs, and cold, invisible remnants. The interstellar gas that once gave birth to new generations of stars is long gone, consumed or locked away in old systems. Star formation ceases. Milkomeda becomes a fossil of light, a graveyard of ancient suns glowing faintly in a universe that has forgotten its beginning. Yet even now, in the far future, motion never stops. Gravity, patient and eternal, continues its work. The smallest stars gradually drift toward the center of the galaxy, their orbits decaying over trillions of years. Some are swallowed by the black hole at the core, adding their mass to its immense heart. Others are ejected entirely, flung beyond the edges of the galaxy into the endless dark. The central black hole grows slowly, its influence spreading ever wider. From time to time, a wandering star or cluster falls inward, lighting the galaxy's heart with one final flare before vanishing forever. Eventually, all that remains are the long-lived red dwarfs, tiny, cool stars that burn their fuel so efficiently they can shine for trillions of years. They will be the last torches in the cosmic night. Around them may orbit frozen worlds, remnants of ancient systems. For a time, these little suns will keep Milkomeda glowing softly, a dim ember in the fading universe. But even they will not last forever. As their hydrogen is finally exhausted, they will cool and fade into black dwarfs, invisible cinders drifting through the dark. By then, time itself will have lost meaning. The galaxy will be ancient beyond imagination, perhaps 100 trillion years old. Its once vivid colors will have faded into shadow. No new stars will form, no new light will rise. The supermassive black hole at its core will dominate the silence, feeding only occasionally when a dying star wanders too close. It will grow massive and quiet, a monument to all that came before. Yet even in this desolate future, the story isn't over. Deep in the quantum heart of matter, strange things still occur. Over unimaginably long timescales, even black holes will begin to fade. Through a process known as Hawking radiation, they will lose energy, slowly evaporating into nothingness. It will take longer than any human mind can comprehend, a number so vast it dwarfs all history. But eventually, even the last black hole will dissolve, releasing its energy as faint particles into the cold void. When that day comes, Milkomeda will no longer exist in any recognizable form. Its stars will have died, its planets turned to dust, its black hole evaporated into nothing. Only the faintest traces of radiation will remain, the final whisper of what was once two great galaxies, two rivers of light that met in a moment of cosmic destiny. The universe will grow dark, cold, and empty. Yet, hidden in that emptiness, the laws of physics, the same laws that once shaped galaxies and stars, will remain, silent but eternal. And perhaps, in some future beyond even time itself, those laws will awaken again, and from the quiet vacuum, a new universe will be born. Here we are, orbiting a modest yellow star halfway out in the spiral arm of a vast galaxy, unaware that we are already part of a cosmic dance, billions of years in the making. The Milky Way and Andromeda are not rushing toward each other with violence. They are moving in slow motion, an elegant waltz choreographed by gravity itself. Every night, when we look into the northern sky, the faint smudge of Andromeda shines as a small oval of light, 2.5 million light-years away. It appears still, quiet, timeless, yet what we see is an ancient snapshot, a ghost from the distant past, already outdated by the time it reaches our eyes. In reality, that galaxy has moved slightly closer, tugged imperceptibly toward us by an invisible bond that spans the emptiness of space. When we talk about this coming collision, it's easy to imagine catastrophe, stars smashing into each other, planets flung into the dark. But that is not what will happen. Space inside galaxies is vast beyond comprehension. Even when two galaxies pass through one another, the chance of any two stars colliding is almost zero. What we will witness, if we could live long enough to see it, is a slow resculpting of gravity, a celestial ballet that plays out over billions of years. The Milky Way and Andromeda will stretch each other into long tidal streams, their spiral arms twisting like ribbons in the wind. Whole clusters of stars will be torn from their homes and set adrift between the two galaxies. From the vantage point of some distant observer, this event will look like two bright whirlpools of light merging, their cores spiraling inward until they become one. To us, standing here on this fragile blue planet, this story is a reminder that nothing in the universe is static. Even our home, the place we think of as stable, permanent, is in motion, caught in the slow flow of cosmic evolution. Every atom in our bodies, every grain of dust, every ray of light is part of this grand cycle of creation and transformation. We live within a momentary calm between the birth of the Milky Way and its future as Milkomeda. Our existence is a brief flicker in that vast timeline. Yet it is from within that flicker that the universe becomes aware of itself. When we gaze at Andromeda, we are seeing our own destiny written in light. It is a glimpse not of destruction, but of renewal. The merging of two galaxies is not the end of their stories, but the beginning of a new one, the formation of something larger, richer, more complex. Without such collisions, the universe would not evolve. Galaxies grow by meeting and merging. Stars are born, die, and return their material to the cosmic sea so that new stars can form. Life itself, on worlds like ours, exists because of these cycles. Because ancient stars exploded long ago, scattering the elements that would become planets and people. The thought of our galaxy colliding may stir unease, but it also evokes wonder. It tells us that we belong to something enormous and alive, a universe that is constantly reshaping itself. Long after humanity is gone, long after our sun fades into a white dwarf and the Earth turns cold, the legacy of our galaxy will continue. Its stars, its remnants, its energy will merge with Andromeda's, and together they will create new worlds, new suns, and perhaps, far in the future, new forms of life to look up at the sky and wonder who came before them. In the end, the collision of the Milky Way and Andromeda is not a tragedy, but a continuation. It is the universe reminding us that endings and beginnings are the same thing seen from different points in time. The same gravity that holds us to the ground, that keeps the moon in orbit and shapes the path of planets, is the very force that draws galaxies together across the vastness of space. We are connected to that force, we are made from it. And though our lives are fleeting, our atoms are ancient, forged in stars that once burned billions of years ago, and destined perhaps to one day shine again in the light of Milkomeda. To truly understand what will happen when the Milky Way and Andromeda meet, we must look beyond the stars and planets, beyond the visible light that paints our night sky. The vast majority of each galaxy is invisible, dark matter, mysterious, unseen, yet overwhelmingly abundant, forms a halo around both galaxies, extending far beyond the spiral arms. This dark matter is not a shadowy villain, but the scaffold that holds galaxies together. It provides the gravitational framework that governs the motion of stars and gas, and it is what ultimately drives the Milky Way and Andromeda together. Without dark matter, these two cosmic giants might drift past each other harmlessly, their encounter far less dramatic. Modern simulations of galaxy mergers use this invisible mass to predict how stars, gas, and dust will behave over billions of years. When astrophysicists simulate the Milky Way to Andromeda collision, the results are breathtaking. First, the outer regions of both galaxies begin to interact. The tidal forces stretch the spiral arms into elongated streams of stars, forming intricate ribbons of light that arc through intergalactic space. Clusters of stars can be torn away entirely, forming orphaned stellar streams that drift independently for millions of years. These streams are the signature of cosmic encounters. They are the fingerprints left behind when galaxies meet. As the cores approach, the inner regions of the galaxies experience stronger gravitational effects. Stars are pulled into new orbits, some moving in tight elliptical paths, others flung into highly eccentric trajectories. Gas clouds collide, compress, and ignite in furious bursts of star formation. The brightest, most massive stars born in this chaos burn hot and die young, ending in spectacular supernovae that scatter heavier elements across the newly forming galaxy. One of the most fascinating aspects of this merger is the behavior of supermassive black holes. At the center of the Milky Way and Andromeda lie these titans, invisible yet dominant. As the galaxies spiral together, their black holes begin orbiting one another, losing energy through gravitational waves, ripples in spacetime first predicted by Einstein and now observed by modern detectors. Eventually, after millions of years, the two black holes merge into an even larger singularity, releasing an enormous burst of gravitational energy. This process shapes the core of Milkomeda and influences the orbits of countless stars near the center. Despite all this violent activity, it's important to remember that stars themselves rarely collide. The distances between them are immense. The solar system, for instance, is unlikely to directly impact another star during the merger. But the gravitational shifts can change its orbit, potentially flinging it to the outskirts of the galaxy or drawing it closer to the dense central region. For planets orbiting other stars, the effects are similar. Some worlds may face new stellar neighbors, others may be sent adrift into the void. The simulations also reveal the long timescale of this cosmic dance. The first encounter will happen in about 4 billion years, with the galaxies passing through each other and temporarily separating. They will then fall back together multiple times over hundreds of millions of years, each encounter increasing the chaos and mixing of stars and gas, until finally the cores merge and Milkomeda settles into a smooth elliptical galaxy. This process, though violent on a cosmic scale, unfolds slowly, almost imperceptibly from the perspective of any individual star system. Through these simulations, we glimpse the incredible elegance of the universe. Even in what seems like chaos, there is order, a predictable, mathematically precise rhythm dictated by gravity, mass, and momentum. The collision of our galaxy with Andromeda is not random destruction. It is a natural, inevitable transformation guided by the unseen forces that govern the cosmos. And through it all, the stars, the suns that light countless worlds, continue their quiet journey, largely unscathed, weaving a story billions of years in the making. Imagine if we could survive long enough, standing on a world still orbiting our sun as the galaxies begin their slow encounter. The night sky would no longer be familiar. The Milky Way's familiar band, stretching like a silver ribbon across the heavens, would twist and warp as tidal forces tugged on our spiral arms. Andromeda, now closer than ever, would swell from a faint smudge into a bright, elongated spiral dominating the northern sky. Its light would brighten gradually over millions of years, first subtle, then unmistakable, until the galaxy blazed like a second sun in the heavens. As the first pass occurs, the spiral arms of both galaxies would stretch into enormous arcs. Some stars would be flung outward, forming stellar streams that glow faintly in the dark. Others would cluster tightly, creating dense, luminous knots. Clouds of interstellar gas and dust would collide, igniting brilliant bursts of star formation. In the night sky, this would appear as sparkling patches of brilliant blue-white stars, a cosmic fireworks display stretching across thousands of light years. Nebulae, born of collisions and supernovae, would shimmer in reds, greens, and purples, painting the heavens with colors that no artist could reproduce. The Milky Way and Andromeda would pass through each other several times over hundreds of millions of years. Each passage would reshape the night sky. From Earth, the galaxy's cores might appear to approach and recede, the tidal streams shifting imperceptibly over generations. Eventually, the merged core would dominate the sky, a luminous, nearly spherical heart glowing in soft gold, surrounded by streams of stars from the disrupted spiral arms. The patterns of the stars we know today would vanish. Orion, Cassiopeia, the Big Dipper, all would dissolve into unfamiliar constellations. New arrangements of stars shaped by the gravitational chaos would emerge, unfamiliar and magnificent. For any observers on distant worlds orbiting other stars, the spectacle would be equally breathtaking. Imagine the sky filled with two galaxies intertwining, their combined light illuminating landscapes, casting shadows, and revealing the vast scale of the universe in a way never seen before. Planets near the central regions might witness unusual flares of brightness from stars forming and dying in rapid succession, while more distant systems would watch streams of stars drifting slowly across the void. Even after the galaxies merge into Milkomeda, the visual changes would continue. The newly formed galaxy would settle into a smoother, elliptical shape, and the stars would distribute more evenly across the sky. No longer would there be the distinct spiral of the Milky Way. Instead, the night would glow with a diffuse, soft radiance, the remnants of the countless stars and clusters scattered during the merger. It would be a sky unlike any we have known, a testament to the immense power of gravity, the scale of time, and the beauty of cosmic evolution. From the perspective of the universe itself, this slow, graceful dance of light and matter is a kind of poetry, a reminder that even the most violent events, collisions of galaxies containing billions of stars, unfold over such vast distances and timescales that the cosmos moves with elegance, not chaos. And for any who watch, the collision is not only a destructive force, but a creator, reshaping, birthing, and illuminating the cosmos in ways unimaginable. Even as the Milky Way and Andromeda weave together in their slow-motion collision, the vast majority of stars will remain untouched. Collisions between stars are exceedingly rare, space is mostly empty, and the distances between suns are immense. But the gravitational chaos will have subtle, profound effects on the planetary systems that orbit them. Our solar system, for instance, could be nudged into a new orbit around the merged galactic core. Its distance from the center might increase or decrease slightly, altering the motion of the Sun through the galaxy and changing the environment of interstellar space surrounding it. Other systems will not be so fortunate. Some may be ejected entirely, flung into intergalactic space like cosmic driftwood, wandering through the darkness far from any galaxy. Planets in these orphaned systems would become cold and isolated, with no nearby stars to provide warmth or light. Yet even in such exile, the laws of physics endure. Planets will orbit their stars faithfully, bound by gravity, and even in the darkest reaches, life could survive if it adapted to the new conditions. Closer to the galactic center, the chaos is far more extreme. Stars may be drawn into tighter orbits around the supermassive black hole, or into dense clusters where gravitational interactions are frequent. In these regions, planets could be stripped from their stars entirely, their paths altered by encounters with nearby suns. Some may crash into other stars, others may be scattered into highly elliptical orbits, and a few may be swallowed by the central black hole. The inner galaxy becomes a place of constant upheaval, while the outer regions remain relatively tranquil. Gas clouds, colliding and compressing, will ignite new waves of star formation, birthing stars that may host entirely new planetary systems. For civilizations in these regions, the sky would be alive with brilliant new suns, and their night skies could be dominated by the glow of massive, short-lived stars. Supernovae from these massive stars would scatter heavy elements, seeding planets with the building blocks of life: carbon, oxygen, iron, much as ancient supernovae seeded our own solar system. For worlds like Earth, the immediate dangers are minimal. Our Sun and planets are unlikely to collide with any other star. Yet, the subtle gravitational nudges could alter the long-term path of our solar system, moving it closer to or farther from the galactic core. Over billions of years, this could change the amount of radiation the solar system experiences from nearby stars, influencing the long-term stability of planetary climates. It is a quiet, slow-motion danger, imperceptible in a single lifetime but significant on a cosmic timescale. Ultimately, the survival of planetary systems during the merger is a testament to the vast emptiness of space. Even amid the grand collision of billions of stars, most systems continue their orbit largely undisturbed. Chaos exists on the largest scales. Galaxies stretch, tidal streams form, black holes merge, but within the vast voids between stars, worlds continue quietly, circling their suns as they have for billions of years. In the end, the cosmic collision is both destructive and protective, reshaping the galaxy while allowing its smallest components, the stars and planets, to persist, survive, and perhaps continue the story of life long after the Milky Way and Andromeda have become one. As the Milky Way and Andromeda intertwine, Their stars begin to mix in a slow, graceful swirl. The orderly spiral patterns of old give way to elongated streams, arcs, and bridges of stars connecting the two galaxies. Amid this chaos, star clusters, dense groups of stars bound together by gravity, experience profound change. Some clusters are torn apart, their stars scattered across the newly forming Milkomeda. Others are compressed and reshaped, their density increasing as gravitational tides pull them inward toward the merged galactic core. Globular clusters, ancient and tightly bound spheres of stars that orbit the outer regions of both galaxies, play a fascinating role. These clusters, many of which formed over 10 billion years ago, survive the merger largely intact due to their strong internal gravity. Yet their orbits are dramatically altered. Some may be sent spiraling toward the center of Milkomeda, while others are flung into the outer halo, forming a vast population of clusters in new, unexpected locations. The halo of Milkomeda, far more extensive than that of either parent galaxy, becomes peppered with these stellar fossils, remnants of a past era, silently orbiting in the dark. The stellar populations themselves begin to mix. Older, red stars from both galaxies mingle with younger, blue stars born in collision-triggered starbursts. The inner regions glow with new activity, fueled by the compression of gas clouds, while the outer regions retain older populations from the original galaxies. Over hundreds of millions of years, the distinction between the Milky Way and Andromeda stars blurs. They form a single, coherent population, orbiting the center of Milkomeda, unified by gravity, yet carrying subtle differences in composition, the chemical fingerprints of their origins. Clusters of stars may collide or merge under gravitational forces, forming new, unusually massive clusters. Some may survive for billions of years as brilliant globular clusters, glowing like jewels in the smooth light of Milkomeda. Others are stripped of their stars, leaving behind faint streams that trace the violent history of the merger. These streams are the cosmic scars of collision, observable to any future astronomers who might peer into their galaxy with advanced telescopes. Meanwhile, the densest regions near the central black hole see their own spectacular evolution. Stellar populations here become compressed, some forming temporary rings or disks of stars that orbit the core together. Supernovae enrich these regions with heavier elements, creating fertile grounds for future star formation and adding complexity to the chemical makeup of the new galaxy. Milkomeda's core, once two separate regions of intense activity, becomes a single, dynamically vibrant hub of light, motion, and energy. In the end, Milkomeda is not just a merger of galaxies, it is a merger of histories. Stars that formed billions of years apart in different galaxies are now neighbors, orbiting together in a new gravitational community. Ancient clusters survive, new stars are born, and the galaxy as a whole emerges more massive, more luminous, and more chemically diverse than either progenitor. This is the enduring beauty of galactic collisions. Destruction gives rise to creation, chaos gives rise to order, and the universe continually rewrites its own story across scales both enormous and intimate. Over billions of years, the turbulent aftermath of the Milky Way to Andromeda collision gradually calms. The dramatic tidal streams fade, stars settle into new orbits, and the galaxy's structure stabilizes. The once distinct spiral arms dissolve into a smoother, more uniform shape. Milkomeda emerges as a massive elliptical galaxy, a glowing sphere of stars, luminous and dense in the center, thinning toward the edges. Its core, dominated by the merged supermassive black hole, shines with soft brilliance, while the halo of stars and globular clusters extends far into the dark, a faint ghostly sphere surrounding the galaxy. Unlike spiral galaxies, Milkomeda rotates more slowly. Its stars no longer orbit in neat, flat disks, but instead follow elongated random paths around the galactic center. This dispersion reduces the galaxy's angular momentum, producing the rounded, ellipsoidal shape characteristic of mature elliptical galaxies. The inner regions remain dense, with tightly packed stars orbiting near the central black hole. Further out, stars are spread more thinly, forming a vast halo that can extend several times the diameter of the original Milky Way or Andromeda. The chemical diversity of Milkomeda is striking. Older red stars from the Milky Way mix with similarly aged stars from Andromeda, while younger blue stars born in collision-triggered bursts remain concentrated in the inner regions. Supernovae from these young stars distribute heavy elements throughout the galaxy, enriching its interstellar medium and creating pockets of material that could form planets or future star clusters. Even as the rate of star formation declines over time, the galaxy retains a layered history encoded in its stars' compositions and orbits. Globular clusters, surviving from both progenitor galaxies, now orbit Milkomeda in wide paths. Some reside near the central core, drawn by its immense gravity, while others drift through the outer halo, forming a population of ancient isolated stellar islands. Streams of stars that were once part of tidal tails slowly disperse, blending into the general stellar population, leaving only subtle traces of their violent past. These remnants are faint, but they serve as cosmic fingerprints, clues to the dramatic history that shaped Milkomeda. Gas and dust, once abundant in both galaxies, are largely exhausted or consumed. The dramatic starbursts triggered during the collision have long since ended, and without a fresh supply of cold gas, new star formation slows to a near halt. Milkomeda becomes a quiet galaxy, its remaining stars aging gracefully. Blue, massive stars burn out quickly, leaving behind a dominant population of long-lived red and yellow stars. The galaxy glows steadily, more serene than its spiral progenitors, yet containing within it all the energy and history of two vast cosmic cities. Even the central black hole continues to influence its surroundings. Slowly, it consumes the occasional star or cloud of gas that strays too close, releasing faint bursts of energy. These events are rare on human timescales but significant in shaping the innermost regions of Milkomeda. Its presence anchors the galaxy, maintaining gravitational stability and guiding the long-term dynamics of the stellar population. In Milkomeda, the universe demonstrates its ability to transform chaos into order. Two spiral galaxies collide, warp, and intermix, yet the outcome is a single, elegant structure. It is no longer a galaxy of spirals, arms, or streams, but a cohesive, mature system, an enduring monument to the forces of gravity, motion, and cosmic time. Its smooth, elliptical form is the quiet echo of billions of years of movement, destruction, and creation, a living record of the universe's remarkable capacity for renewal. Over the next trillions of years, Milkomeda will enter a profound era of quiet aging. The brilliant, short-lived blue stars formed during the galactic collision will have long since burned out, leaving behind neutron stars, white dwarfs, and black holes. The once luminous galaxy will gradually redden as its long-lived red and yellow stars dominate the light, and the collective glow of Milkomeda will dim. The days of dramatic starbursts and swirling spiral arms will be a distant memory, replaced by a calm, steady galaxy orbiting silently in the expanding universe. Star formation, already slowed by the depletion of gas during the merger, will virtually cease. The remaining interstellar gas will be exhausted or locked in stellar remnants, and without fresh material to collapse into new stars, Milkomeda will grow increasingly static. Its halo, populated by globular clusters and scattered tidal streams, will persist, but the energy within the galaxy will fade. The vast stellar population will age together, a galaxy of elderly suns moving in predictable, elliptical orbits. The supermassive black hole at the core will continue to grow, slowly consuming stars that stray too close. Occasionally, interactions between stellar remnants in the dense central regions may create dramatic, localized flares of energy, but these will be rare and short-lived on cosmic timescales. The core remains a gravitational anchor, ensuring the galaxy's structure endures even as its light fades. Red dwarfs, small and extremely long-lived, will become the dominant population. Their slow, steady nuclear fusion allows them to burn for trillions of years, far outlasting larger stars like our Sun. These diminutive suns will become the last enduring beacons in Milkomeda, hosting planetary systems that may survive long after brighter stars have extinguished. For civilizations that exist in these far future epochs, the sky would appear dominated by a few red suns, quietly illuminating distant worlds in an otherwise dim universe. Meanwhile, white dwarfs, the remnants of medium-sized stars, will cool and fade over billions of years, becoming black dwarfs, invisible in the darkness. Neutron stars and stellar mass black holes will drift through Milkomeda's halo, largely undetectable except through gravitational interactions. Over unimaginable spans of time, Milkomeda will transform from a luminous, chaotic galaxy into a quiet, ghostly system of faint remnants, where motion continues but energy slowly wanes. Even the halo of Milkomeda, once peppered with globular clusters and tidal streams, will age. Some clusters will gradually evaporate as gravitational interactions scatter their stars into the wider galaxy. Streams of stars will diffuse and blend into the background, leaving only subtle gravitational traces of their violent past. The galaxy, though still vast and massive, becomes a dim, ordered system, a relic of its once dynamic past. Through this long cosmic era, the story of Milkomeda reminds us of the impermanence of even the grandest structures. Galaxies collide, stars are born and die, black holes merge, and yet the universe endures. The processes that shape galaxies operate over scales far beyond human comprehension, yet they follow precise physical laws. Milkomeda, in all its faded majesty, is a testament to the elegance of cosmic evolution, a monument to the forces that govern stars, planets, and light itself. Trillions of years from now, Milkomeda will be a galaxy of faint embers. The once brilliant stars will have dimmed or died, leaving behind black dwarfs, neutron stars, and stellar mass black holes drifting silently through space. The red dwarfs, long-lived though they are, will finally begin to fade as well, marking the end of the era of shining stars. The galaxy, though still massive, will be shrouded in darkness, illuminated only by the occasional flicker of dying remnants. At its core, the supermassive black hole, once a turbulent force during the merger, will continue to dominate the gravitational landscape. It will have consumed much of the surrounding matter over billions of years, growing to immense size, yet it too will face the slow, inevitable process of Hawking radiation. Over incomprehensibly long timescales, far beyond the life of any star, even this cosmic titan will evaporate, releasing its mass as faint radiation back into the universe. The remaining black holes scattered throughout Milkomeda will follow a similar path. Over quadrillions of years, gravitational interactions will cause some to merge, forming ever larger black holes, while others drift into the emptiness between stars. Eventually, each will slowly evaporate, leaving nothing but photons and subatomic particles in their wake. The once dense, star-filled galaxy will transform into a nearly invisible collection of faint remnants and energy, a ghostly echo of the vibrant Milky Way and Andromeda that once collided so spectacularly. Planetary systems, if they survive this long, will orbit dead stars or black dwarfs in eternal darkness. Any potential life will have ended long ago, extinguished by the exhaustion of energy sources. The galaxy, once a bustling hub of creation, will become a quiet expanse of frozen matter, drifting in an ever-expanding void. Streams of stars and former clusters will have fully dispersed, leaving only subtle gravitational footprints detectable, if at all, by future civilizations or advanced probes. This marks the beginning of the Dark Era, a time when the universe itself has faded. Milkomeda, now alone, isolated and dim, drifts through the cosmic void with no nearby galaxies visible. The expansion of space has carried other galaxies far beyond the cosmic horizon. Light from distant stars and galaxies can no longer reach Milkomeda. The universe outside is a cold, dark, and silent place. In this epoch, matter is scarce, energy is low, and the once vivid beauty of the cosmos exists only as faint remnants of the past. Even in this darkness, the laws of physics endure. Gravity continues to bind the remnants of Milkomeda together. Black dwarfs orbit silently. Neutron stars drift through the halo, and the few remaining particles of matter follow the paths dictated by their past motions. The galaxy itself becomes a monument to the impermanence of energy, yet a testament to the persistence of structure, an island of matter in a cold, dark ocean of space. In the unimaginable future, Milkomeda will become nothing more than an echo, a ghost of two galaxies that once collided, merged, and reshaped the universe around them. Its story, encoded in the motions of stellar remnants and the faint radiation left behind, will eventually fade entirely. Yet in that fading, it reflects the most profound truth of the cosmos, that creation and destruction are inseparable, that all structures have lifespans, and that even in the darkest era, the universe continues to evolve according to immutable laws. The collision of the Milky Way and Andromeda is more than a story of stars and galaxies. It is a story about perspective, time, and the place of life in the universe. From our vantage point on Earth, we may never witness this grand event directly, yet it unfolds on a scale that dwarfs human imagination. It reminds us of the immense timescales on which the cosmos operates. Billions of years for a single galactic encounter, trillions for its aftermath. In contrast, our own lives are but fleeting moments, a heartbeat in the grand rhythm of the universe. Yet this perspective need not diminish our significance. Every atom in our bodies was forged in the hearts of stars, some of which may have exploded in galaxies that will one day merge to form Milkomeda. We are literally the children of cosmic collisions, the products of processes that span billions of years and unimaginable distances. The merging of galaxies, then, is not just a physical event. It is a reminder of the continuity of matter and energy, the cycles of creation and destruction that make life possible. The night sky itself teaches humility. Stars that seem eternal are temporary. Galaxies that seem immutable are in constant motion. The Milky Way's spiral arms, our familiar constellations, even the sun itself, are all transient. The eventual collision with Andromeda reminds us that change is the universe's only constant. It prompts reflection on our place, not only in space, but in time. We occupy a unique moment after the formation of the Milky Way and Andromeda before their ultimate union. It is a fleeting, precious slice of cosmic history. At the same time, the eventual creation of Milkomeda offers a sense of continuity and hope. Even as stars die and galaxies fade, the universe regenerates. Collisions create new structures, new stars, new possibilities. The violence of cosmic evolution is also the seed of creation. Just as the merging galaxies produce new stars and planetary systems, life itself may arise anew, in forms we cannot imagine, in epochs far beyond our own. In this, there is a profound lesson. Endings are rarely final. They are transformations, transitions from one state to another. From an existential perspective, the Milky Way to Andromeda collision challenges our sense of permanence. It asks us to consider the impermanence of all things, planets, stars, civilizations, and yet it also demonstrates the enduring patterns of the cosmos. Gravity, motion, and energy continue to operate, creating order from chaos, sculpting beauty out of destruction. Our lives, brief though they are, participate in this ongoing story. Every observation we make, every discovery, every understanding of physics is part of the universe becoming conscious of itself. In the end, the collision is both terrifying and awe-inspiring. It is a reminder that we live in a dynamic, ever-changing cosmos. And yet, it is also a testament to the elegance, resilience, and interconnectedness of all things. The galaxies that will merge billions of years from now are distant, but their story is our story too. It is the story of matter, energy, life, and consciousness. A reminder that we are part of something larger, something eternal, unfolding in the vast theater of space and time. How do we know the Milky Way and Andromeda will collide billions of years from now? The answer lies in the remarkable ingenuity of modern astronomy. For centuries, humans observed the stars, noting their motion and mapping the heavens. But it is only in the last 100 years that we have developed the tools capable of measuring the subtle motions of galaxies across millions of light years. Telescopes like Hubble have allowed astronomers to determine Andromeda's velocity toward us, approximately 110 kilometers per second. That may seem fast, yet in the cosmic scale, it is a slow, deliberate drift, ensuring the galaxies will meet not in an instant, but over billions of years. Observations alone are insufficient. The collision is predicted through sophisticated computer simulations that model the gravitational interactions of billions of stars, gas clouds, and dark matter particles. Astrophysicists create virtual galaxies, assigning positions, velocities, and masses to each component, then let gravity and physics run the simulation forward over billions of years. The results consistently show the Milky Way and Andromeda passing through each other multiple times before finally merging into a single, massive, elliptical galaxy, Milkomeda. These simulations also allow scientists to explore the dynamics of star clusters, the movement of gas clouds, and the fate of black holes during the merger. They reveal tidal tails stretching across intergalactic space, regions of intense star formation, and the eventual settling into a smooth, elliptical shape. Without these models, we could not understand the scale, duration, or beauty of the process. They provide not just predictions, but a cosmic narrative that we can follow from our small corner of the universe. Gravitational studies complement these simulations. By observing the motions of stars within the Milky Way and Andromeda, astronomers can infer the distribution of dark matter, the invisible substance that dominates the mass of both galaxies. Understanding dark matter is critical. It is the invisible hand guiding the merger, dictating how galaxies approach, how stars orbit, and how the final galaxy will settle. Without precise measurements of mass and gravity, our predictions would be incomplete or inaccurate. Together, these tools, telescopes, computer simulations, and gravitational studies allow humanity to peer into the future. We can visualize the first pass of Andromeda across the Milky Way, predict the formation of new stars, and anticipate the eventual birth of Milkomeda. What seems impossible to witness in real time becomes comprehensible through science. We can imagine standing on a world billions of years from now, seeing two galaxies intertwine, not because we will be there, but because mathematics, physics, and observation let us travel across time and space in our minds. In essence, the story of the Milky Way to Andromeda collision is a testament to human curiosity. It is proof that with careful observation, precise measurement, and the power of computation, we can understand events unfolding on scales far beyond our own experience. We are, in a sense, participants in the universe's grand narrative, observers capable of comprehending the past, predicting the future, and marveling at the cosmic forces that have shaped and will continue to shape our galaxy and all the stars within it. In the end, the collision of the Milky Way and Andromeda is both a scientific event and a story of cosmic scale, a story that stretches across billions of years, uniting galaxies, stars, planets, and even the dust from which life arises. It is a narrative written in gravity, light, and time, unfolding far beyond the span of a human lifetime, yet intimately connected to everything we know. From our vantage point on Earth, it may seem distant and abstract, but in reality, we are part of the same universe that will one day witness this grand merger. Through observation, simulation, and theory, we have glimpsed the future, the first approach of Andromeda, the tidal distortions of our spiral arms, the starbursts ignited in colliding gas clouds, and the eventual formation of Milkomeda, a smooth, luminous, elliptical galaxy. We have seen how planetary systems like our own may survive or drift, how globular clusters and tidal streams preserve memories of the past, and how supermassive black holes dominate the central core, shaping the orbits of countless stars. This story also reminds us of the immense scales of space and time. The collision will unfold over billions of years, a slow-motion dance almost imperceptible to any single observer. It challenges our sense of permanence, showing that even galaxies are temporary structures in a dynamic, evolving universe. And yet, in this impermanence, there is continuity. Matter is never destroyed. It is reshaped, recycled, and reborn. Stars die, but new stars emerge. Galaxies collide, but new galaxies are born. Life, energy, and complexity persist through cycles that far exceed our comprehension. The Milky Way Andromeda merger is a profound example of creation through destruction, order arising from chaos, and the delicate balance of cosmic forces. It is a reminder that our own existence is intimately linked to these grand processes. Every atom in our bodies, every element essential for life, was forged in stars, some of which may have existed in galaxies that will one day merge to form Milkomeda. We are, in a very real sense, the children of cosmic collisions, the products of a universe that evolves, transforms, and persists. And when Milkomeda finally settles, quiet and luminous, in a universe slowly expanding into darkness, it will carry within it the history of two ancient galaxies. Its stars will trace the paths of their ancestors, its globular clusters will preserve remnants of their past, and its black hole will mark the center of a new cosmic order. Even as the universe fades over trillions of years, Milkomeda's story will remain written in the orbits of stars, the faint radiation of remnants, and the enduring laws of physics that govern everything. Ultimately, this story is more than a tale of galaxies. It is a meditation on time, scale, and perspective. It reminds us that the universe is vast, dynamic, and astonishingly beautiful, and that we are part of it, observers, participants, and inheritors of its legacy. The collision of the Milky Way and Andromeda is a future we may never witness, yet it teaches us about the forces that shape reality, the inevitability of change, and the astonishing continuity of matter and energy. It is the story of the cosmos itself, relentless, creative, and eternal. And as we look up at the night sky tonight, perhaps we can see Andromeda as it truly is, not just a distant smudge of light, but a partner in a cosmic dance, destined to meet us, to reshape our galaxy, and to continue the grand story of the universe long after we are gone. The collision is both an end and a beginning, a testament to the power, beauty, and inevitability of the cosmos, and a reminder that we are all part of something far larger than ourselves.